All right, so in this application of solving trig equations, we have an example where we're trying to identify when the sun rises at 4 a.m. So if you look, we know the first sunrise in the US is observed from the Cadillac Mountains on Mount Desert Island in Maine. What's important that the problem tells us is the model T of m equals 1.665 sine pi over 6 times n plus 3 plus 5.485. I know, not pretty numbers, but hey, most of the equations out there that model things are not going to be that pretty. But that's okay, because we'll know how to work with it. Okay, so what's important here is what our variables represent. T is the hours after midnight, and m is a number of months after January 1st. So we want to know when the sun rises at 4 a.m. 4 a.m. happens to be 4 hours after midnight, so T equals 4. So what we'll do is we'll basically be putting 4 for T of m, and we're solving for m because we want to know the number of months after January, right, where the sun will rise at 4 a.m. So 4 equals 1.665 sine, and this is where I know it can be a little weird looking, but sine of pi over 6 times m plus 3, that whole thing is what we're actually doing sine to. So I'm going to rewrite this with a bracket because I don't actually love how that's not written in the model, but that's the model that we were given. So we want to work with it. So this is saying take pi over 6 times m plus 3. And that entire quantity is what we're going to do sine to. And then we're going to add 5.485 to the end there. So we want to solve this. So what I would do is just start solving like I normally would, right? Take away this 5.485 because remember we want to isolate the sign. So then I'm going to get negative 1.485 equals 1.665 sine of that entire thing. And slowly just work my way toward getting sine by itself, right? So I'm going to divide 1.665. And it's actually okay if you leave your answer as a decimal here, but my calculator will happen to give me the equivalent fraction, which is a lot nicer to write, but you can leave this as negative 1.465 over 1.665. Just please don't round it. Remember, we round once and we round at the end. Okay, so this happens to reduce down very prettily to negative 33 over 37. So if your calculator does that for you, great. If not, you can leave it as negative 1.485 or 1.665. Just remember, don't round anything yet. And now we've got sine all by itself. Great, because what we want to do is we don't want sine, right? I want to get m. M is trapped inside the sine function. So we're going to do the inverse of sine. So I'm going to take the inverse sine to both sides to get rid of the sign here on the right, and we're going to get pi over 6 times m plus 3, right? So pretty straightforward up to here, okay? What's tricky here is when you're doing the inverse sine of negative 33 over 37, if you do it in your calculator, we'll get a single answer. So if you do this in your calculator, what you'll get is negative 1.10151136, and it goes on and on. So there's no nice fraction for this. So in this case, this is what I do to represent. I know it goes on forever. That's kind of as exact as it gets for me. However, is that the only place where sine, where we could get, is that the only value? I guess that's what I'm getting at. Is that the only value of the inverse sine? Well, remember what we talked about when we talked about solving your trig equations earlier. Where is sine negative? If we're looking between 0 and 360, all students take calculus, so sine is positive in the first quadrant, sine is positive in the second quadrant, but not in the third and the fourth quadrant. So that means we have two possible places for this inverse sine. And oh, I forgot to say one big thing. If you're not getting this negative 1.1015113666, make sure you're using radians, because that pi over 6 tells us we've got to use radians. So if your calculator is not set to radians, you're not going to get the right value. All right, but moving back to this. So what is this negative 1.101 when we talk about an angle? That's going the opposite direction. That's going clockwise. So this is negative 1.1015, etc., right? So its reflection in the third quadrant would basically be pi plus 1.1015, etc., because we want to add that on to that 180. So there's actually two possible answers to inverse sine of negative 33 over 37 because of, right, if you're thinking about one period, how often we get the same y value, it's going to be twice. So for that value, right? So adding pi to to positive 1.1015113666, we get 4.23410442, etc. And again, here I'm adding it because I'm adding the reference angle. The reference angle is a positive angle with the x-axis, so I want to make sure I'm adding that reference angle on. So this is equal to pi over 6 times m plus 3. So basically we've got two equations to solve now. So negative 1.10151136 equals pi over 6 times m plus 3. So I can multiply both sides by 6 over pi or divide by pi over 6. It's the same thing. So I'm going to multiply this by 6 over pi. Okay, so that's going to give me 6. And then I'm left with m plus 3. And oops, I hit the wrong button in my calculator because I was like, wait, 6 shouldn't be right. This should actually be negative 2.1037317, etc. And now let's subtract the 3 to get approximately negative 5.10373. So that's one possible answer. We'll worry about interpreting that in a moment. Let's go ahead and find the second answer. So I'm just going to scooch my space over here. So our second equation, 4.23410442 equals pi over 6 times m plus 3. Solve it the exact same way, right? I'm going to multiply both sides by 6 over pi because multiplying by the reciprocal is the same as dividing by the fraction. So what do we get here? It looks like we get 8.1. Oh, sorry, it's not writing. 8.1037317746, etc. equals m plus 3. So now subtract the 3, and we're going to get positive 5.1037317, etc. So that's approximately m. So we have two different values for m. And now in our application, we have to do one last bit of critical thinking, is we have to think, okay, what does this mean? So remember, m is a number of months after January 1st. So if we're going backwards, this means we want to go 5 months, a little over 5 months before January 1st. So count your way backwards. So January, December, November, right? So it'll be December, November, all the way back to approximately the end of July, right? Because it's a little bit over 5 months before January. So December, November, October, September, August is exactly 5 months, but it's just slightly over. So this is approximately the end of July. Okay, now if we look at the other side, it's positive. So it's a little over 5 months after January. So you're counting January, so next is February, March, April, May, June. So it'll be early June. Okay, so we just want to summarize that up in a sentence, and then we're all done. So the sun rises at 4 a.m. at the end of July and early June. So there we go. So there's one problem just like this for you guys to try as well, just slightly different because we're looking at the number of days after January 1st, but the same idea. So go ahead and pause and try it if you'd like. Otherwise, I'm going to continue on with this video and actually explain the U-try problem. So unpause whenever you're ready, or just keep going. Okay, so now it's basically the same situation, but instead of looking at months, we're looking at number of days. So to me, that's just kind of a pain at the end because I can count number of months. Days is a little bit harder. I'll whip out my calendar to figure that out. But otherwise, it's the same idea, right? We're looking at a model now that tells us the number of hours of sunlight in a day at this mountain. And we know that there are 12 hours of sunlight. So hours of sunlight is represented by H. So H equals 12. So then when I look at my model, h of d equals 3.31 sine of all that stuff, I'm basically substituting in 12 for h. And then I want to solve this just like we did before. And remember, be careful here. I don't love the way it's written, but this sign is of the entire piece after it. So pi over 182.5 times d minus 85.25. That whole thing is what sine is operating on. And then it's just going to be just like before. We're going to isolate the sign, do our inverse operation, thinking about how many answers there are, and then, of course, solving for d this time and interpreting that. So let me go ahead and show you what I get when I isolate sine. All right, so you want to go over those steps again. Feel free to kind of rewind or go back because I explained kind of that in the solving process earlier, but just basically getting a sign by itself. And remember, if you want to simplify this fraction, this negative 0.22 over 3.31, you totally can, but because I'm going to put that in my calculator anyway, I'm not going to bother because it's not my final answer, so I'm not going to worry too much about that. So once we get here, remember, we want to do the inverse of sine. So we're going to do inverse sine of negative 0.22 over 3.31 equals pi over 182.5 times d minus 85.25. And once again, we have to ask ourselves, okay, sine of a negative angle, or sorry, not a negative angle. We're looking for an angle where sine is negative. So where is that possible? So if you think about all students take calculus, which tells us all the positives, sine is not positive here in the fourth and the third quadrants, just like before. So what I want to do is I'm going to be looking for this reference angle here first. So I'm going to put that in my calculator. So inverse sine of negative 0.22 over 3.31 is going to give me approximately this angle negative 0.0665142.908. All right. And remember, this is in radians, so make sure your calculator's in radians. So if we want to figure out what that reflection is here on the left, remember this is pi, and we're going to add the reference angle to it. So this will be pi plus 0.0665, etc. So my two possibilities here for the inverse sine of negative 0.22 over 3.31 are 0.0665142.908, and it kind of goes on, or when I put that in and add pi to it, I get 3.208106944, etc. So we have two possible answers. So that's going to equal pi over 182.5 times d minus 85.25. Okay? And then we can split that up into two different equations and solve just like before. So let me go ahead and show you those solutions. All right, so solving that basically just like how I solved that first, the example earlier. So we'll get approximately 81.34608 days, or 271.613918 days. So here's where I don't like the days. I'd rather have months because it's much harder for me to figure out the days without a calculator. So I did just kind of take out a calculator and counted the days. And you guys can do that too, right? It's just a little bit harder to do, I think, mentally, because every month has a different number of days. So it's not like you can say, okay, every month is 30 days, so I can just divide by 30. You'd actually need to go through and count the days. But if you did, you'll realize this 81 days is actually just a little over 2 months. So this is going to be late March. And 271.61 days is around late September. Okay, so to answer the question, when are 12 hours of sunlight, we can say there are 12 hours of sunlight. In late March and in late September. And that's it for this example of an application. Thanks for listening.